Welcome everyone, and thank you for joining us. I'm Brenda Dentinger from BioPack, and I'll be your moderator on today's webinar, Guiding Helicopter Pilots with fNIRS and Large Language Models. We're really excited to bring you this topic and speaker today. Dr. McKendrick wants to share how he used fNIRS technology in applied research to develop a cognitive workload classifier and deliver real-time guidance to helicopter pilots. And he wants you all to understand what's possible with fNIRS technology and how it can be used in different industries to develop products. Today's webinar is being recorded. We'll send out a link as soon as possible during the webinar. If you have any questions, please submit them and I'll share them at the appropriate time. Before we start, I have a little background information about BioPack. BioPack develops high-quality scientific tools that allow you to measure physiology and cognition anytime, anywhere, and with any subject. We've been in business for over 30 years, and 99% of the top universities use BioPack products, and many of the largest technology, consumer products, and pharmaceutical companies also use our products for development and validation. And by the way, we've been cited in over 55,000 publications. Now, the equipment that we use in today's webinar, is fNIRS devices. Dr. McKendrick and Tim will talk more about this technology, but I wanted you all to see what the system options look like. It includes an amplifier, a sensor, software, and of course you can pair this with other physiological data collection to make your research multimodal. We host a biennial human physiology conference event. Registration is now open. We'll be hosting this event again in July 2025. It's at UC Santa Barbara in California. We'd love to have you join us. It's a great opportunity to get hands-on experience with all BioPack devices, including the devices in today's webinar. Early bird pricing is ending at the end of this month, so that's tomorrow. So if you want to save over $100, go ahead and register by the end of day tomorrow. And here are a few of my favorite photos from the 2023 event. So save the date and meet us in California. Now, on to our presenters. As I mentioned, we have Dr. McKendrick. He is an applied cognitive scientist at Northrup Grumman. Over the last 8 years, he developed a system to analyze mental workload in pilots to provide real-time feedback. He obtained his BA in psychology at Rutgers University and a PhD in psychology from George Mason University. His research is focused around human factors, cognitive psychology, cognitive neuroscience, behavioral psychology, and neuropsychology. Welcome, Dr. McKendrick.
Hi, Brenda. Thank you for having me.
We also have Tim Cook, product expert and domestic sales manager at BioPack. Tim has his MS in health and human development. He has over 18 years of experience in the life sciences and physiology monitoring industry. He's very well versed in setting up and running student lab learning systems, and always has a ton of great information to share. Welcome, Tim.
Good morning.
All right, Dr. McKendrick, we're going to start with you. I'm making you presenter.
Okay, sounds good. Just let me know if you can see my screen.
Everything looks great.
All right. Well, I guess it's okay. It's still morning for me. Good morning, everyone. Just a quick overview. So what I'll be talking about today is I'll be going through a couple of the current system challenges that I'm seeing for some of the capabilities we're trying to develop. What that means from the perspective of a human state control system, the measurements that are relevant for such a system, how to translate those measurements into system states that you can then use for control, and then talk about that the application to a guidance system, and show you guys a validation study, and then kind of return to some of the earlier concepts so I can talk about the things that I'm personally focused on for next steps. So a lot of the times when we're talking about the frontiers of science and engineering, it often helps to start with an example from science fiction. I'm a huge fan of a very semi-popular but not incredibly popular video game franchise called Armored Core. And Amazon recently released an episode starring Keanu Reeves highlighting the franchise. And it's essentially a large mechanized combat robot that the premise is requires a very deep physiological connection to the human operator, neurologically and physiologically, to actually operate this system. And it kind of begs the question of, given all the sensors and capabilities that we have today, why are we so limited in our ability to engineer, design, and deploy such systems? And that's some of the concepts that I want to begin to explore today and kind of talk about. So some of the reasons why I think systems like this that deeply embed a human operator into a physical system or a cyber physical system have to do with a couple of things. There's current beliefs that it just takes too long to set up the appropriate sensor apparatus to embed a human. Most people, unless they're kind of captive audiences like sometimes we see in the military, simply wouldn't be accepting of that type of integration with a system, and it can potentially be uncomfortable. I can't really address the acceptance component, but I can say in the studies that I'm going to talk about, we often had imaging and integration with subjects for over 8 hours, and set up generally in how we did it, which implements both the imaging device and a virtual reality system, can be done in anywhere between usually less than 5 minutes. Then there's the question of efficacy, of can we measure the right components from the human in a sufficient way? Can we then infer the appropriate states that are going to give us reliable performance output? And then can we tune the system such that the system of systems is reliable? And that's kind of where we get into but are things good enough already? Do we need new imaging technologies? Can we interpret the data that's even coming from new imaging technologies that are doing, sub-millimeter measurements of neural activity? Which then brings us to the notion of, do we even have sufficient theory within the notions of doing real-time control of a human-machine system to facilitate the development, design, and test of such a system, do that research and validation? I think some of the evidence I'm going to present today suggests that we're getting to a point where we can do the appropriate measurement and state inference. We're certainly at a point where we can begin doing the research. But those are the next steps of doing the research to then be able to appropriately validate and certify such systems, demonstrating their performance efficacy. So I'm going to quickly just do a short review to highlight the differences between, say, a diagram like this, which represents a current, let's say it was a flight control system. The human operator provides some kind of command input to like the stick. That is generally read by a systems controller, which has which has some representation of the stable and unstable dynamics of that system, and then we'll make modifications to that control input to then produce a specific output of the system. It will monitor that output and make any adaptations it needs to make. And then the human operator, as the outer loop controller, will then perceive those modified system outputs relative to the input that they provided to the system. That's how most modern flight control systems work, although this is a highly simplified example. The kinds of systems that we're talking about that provide a deep embedding is providing this other almost outer loop to these two inner loops regarding the constant real-time assessment of the cognitive state of the operator, how that would then feed some human control layer, which then has a number of key outputs. Namely, it can potentially modify the underlying dynamics of the system controller, which is modifying the open loop dynamics of the system. And at the same time, it can modify the feedback and then potentially some of the control dynamics of the human operator, who's also monitoring the feedback of the system. So the feedback to the operator might be in imagery, auditory alerts, haptic feedback, whatever is required. And modifications to the system might be how some of the flight dynamics are modified. Currently, those were done statically through initial human testing with a person, but we could imagine a world where those dynamics are more fluid based on the cognitive state of the operator. So a big challenge with this, as kind of mentioned earlier, is, well, how do we provide the measurements of these cognitive state inputs to a controller such that it can provide appropriate input to both the system controller and the human operator? So in our research, the method of measurement for the raw neural signal, or for the neural signals that we're trying to infer, was from fNIRS. So fNIRS is a measure of central nervous system. It's specifically looking at the metabolites in the brain associated with oxygen, namely the retention of oxygen within hemoglobin. And so essentially what happens is infrared light is emitted by a sensor, and then that the absorption of that light through the different substrates that it's passed through is then monitored by a detector. Different wavelengths of light are used. That's predominantly so that we can differentiate between relative changes in the oxygenated, deoxygenated hemoglobin and water. And then those are converted into those relative changes. And commonly what's done with fNIRS is it's used to measure the blood oxygen level dependent response, which is been observed that in the presence of neural activity, there's a large influx of oxygenated hemoglobin, and that is then also correlated inversely with a decrease in deoxygenated hemoglobin. One of the key differences for the system that I'll be talking about today is we actually do not base our workload classifier on the bold response. Our classifier is generally attempting to monitor and infer elements of the hemodynamic response that are occurring prior to the bold response. Some people refer to this as the initial dip. So we're trying to do instantaneous changes in oxygenated or deoxygenated hemoglobin as opposed to the delayed response associated with the bold response. The other key thing that I now want to get into is within the workload prediction literature, very commonly what you will see is a conversation around load. High load versus low load. I think this is a legitimate conversation, but I believe it has led to some deficiencies in how we estimate real-time states in human operators. And the reason is I want to kind of start with an analogy from the concept of pain. So we know that, let's say I were to take a cold compress or some other implement used in kind of calibrating pain response. We know that we can apply additional pressure over time, and we know that in different individuals, there is a different pressure level at which they will acknowledge they are perceiving pain. Additionally, those individuals also have different pain tolerances. So there's another level of pressure where we will acknowledge that is kind of our threshold of pain. And these capacities, in terms of that, the very real state of pain that we are in is related to fundamental traits of the person experiencing the stimulus. And pain is a common thing we're all used to. And the kind of analogy or a good model I believe that exists that was presented by Young, Wickens, Hancock, and others follows something very similar, is that given a stimulus, some kind of task demand, some kind of demand of cognitive processing, we all have traits associated with different neural processing architectures that then interact with that task demand. And it is that interaction that then produces the mental workload state that we're in. Is it within our demand, our ability to process? Is it underwhelming to us, or is it overwhelming to us? And one of the things that we had been focused on in a 2019 paper that we published was if you looked at the majority of the workload literature on predicting workload states, almost unanimously, every paper would make the following assumption as kind of graphically depicted in the upper right, namely that task demands were approximately equivalent to workload. This only works in a single classifier model where you're modeling a single individual. From the perspective of the classifier, task demands do fundamentally for that individual equate to workload. But the second you explored in a group context, unless you've done some kind of study beforehand to ensure that all these individuals share the same kind of cognitive traits. There is no legitimate reason, based on this relatively straightforward model, to ever believe that task demands equate to mental workload. I think we all can imagine very simple and real scenarios where two different individuals can experience the same thing from a cognitive perspective, whether it be doing a math test, remembering a grocery list, where the same stimulus is presented, but different people experience the cognitive load of that stimulus differently. To further validate this, we wanted to create a psychophysical task based on a real environmental task that's commonly done within many civil and military domains. And so one of those is wide area surveillance reconnaissance. So essentially, we devised a task that forced individuals to remember a set of rules for a specific target. So those rules defined what the target was among many distractors. And then given a open characteristic of that target, how should you respond to it? So you could imagine, like, find me the truck. Then dependent on whether the truck is red, you do this. If the truck is blue, you do that. And we created a simple task around that. And we wanted to then afford very fine-grained control of load, so we could manipulate the memory rules that were required for each individual. We could then also manipulate any attentional demands, so number of distractors, features and characteristics of distractors that are shared with the target stimulus, as well as manipulating the noise around any of the characteristics of the target via desaturation of color, blurring certain symbols, blurring shapes, things like that. And what this allowed us to do is have very, very fine-grained control over these three core kind of cognitive facets of cognition, so that we could both explore them independently and then eventually create classifiers that looked at their interactions. So focusing on the memory version of this task, which was the first one we did and the first one we published on, we started with a relatively two straightforward models of what it might be to talk about workload capacity. So the one on the left is kind of like a stress strain model, where eventually as workload or as task demands increase, given a certain human's capacity, you'll see an asymptote, which is representative of their capacity, and then that can be used to kind of interpret and label the workload state of that individual given a stimulus. The other is more of a logistic model or a RASH model, commonly used in educational testing to determine an individual's capacity to handle a task, or sorry, an item on a test. And this makes a similar assumption where if you can get an item 50% right, an item of the time, that's essentially equivalent to your capacity to handle items within that concept. So we employ that as well. And the upper two plots represent the models. The bottom two plots represent the actual observed data across, I think this is the smaller version of the data set, which is like 30 individuals. We eventually moved it up to 60 individuals. And the black dashed line is representative of kind of like the group level model. But then the red lines are the individuals. And those are parameterized given a random effects model. And what we see is that in both cases, performance fits these models really well. Each individual has kind of their own asymptote or point of subjective equality, where essentially they have a capacity. And then we wanted to use that for devising labels. So applying those methods of kind of saying, okay, if a task stimulus is beyond your mental capacity to handle and you make an error, we're going to say you were in an overloaded cognitive state for your memory system in this example. However, if at any point you were able to handle the stimulus and you didn't produce an error, we were going to say you were in a nominal or a nominal cognitive state. And then in the kind of other rare case, where if the stimulus, as far as we could tell, was well within your capacity as we modeled it, but you made an error, in this case, we labeled that as underload, just to suggest that there's no reason you should have made an error, but there was some misallocation of mental resources or error of processing beyond just the sheer capacity of the stimulus that forced an error. And what I want to highlight here is the difference between the graph on the far right, where it's showing an increase in task demands, and the proportion of states that individuals were then labeled in. So this is the canonical model that is generally used in workload prediction development. And you can see it's just basically saying, okay, when the task is hard, everybody's overloaded. When the task is medium, okay, we're going to say that that's, medium load. And when the task is easy, we're going to say that's low load, or in our case, we label it as underload. And that's drastically different than when you actually look at how people perform on the task and then apply a principled model based on their trait capacities to their performance to then produce those labels. And importantly, what we found when we did this is that we were able to develop labels based on those states that we then used for training a supervised machine learning algorithm. So essentially the process for this is then you take the fNIRS time series as input, which is provided to the supervised machine learning algorithm. It is then going to try to predict those labels that we created from the model. And then dependent on those errors, it will tune itself to then try to produce a model that best predicts those cognitive state time series labels. So I want to kind of talk about a certain method that we've been deploying for doing supervised machine learning. The reason I want to talk about this method is we're using it in a lot of areas, and it's been gaining a lot of interest in other fields related to equation discovery. It has a number of very interesting advantages that not only is it able to fit complex functions, but fundamentally it leads to interpretable models. They are generally parsimonious, meaning that they're as simple as they need to be, but no more simple than they have to be. And fundamentally, they contribute something to the research literature where when you learn a model like this, a expert in the field can then compare the features in the model and how those features interact via a symbolic expression to the literature. So what I'm talking about here when I refer to symbolic regression is a special field of evolutionary computing, which uses a stochastic population of, in this case, programs to try to minimize an error function, which then represents that relationship between an fNIRS input signal and the cognitive state labels. And the output that this system will produce is essentially an expression tree, as shown on the right, which is some kind of symbolic expression that formulates that relationship. In our case, what we essentially used is a method referred to as grammatical evolution. So in this case, the way that the algorithm learns and forms individuals within the stochastic population for evolutionary computing is we define what's called a context-free grammar. So that grammar represents a set of variables, expressions, or operators and transforms via a set of rules that the evolutionary algorithm can use to then produce programs. And in this case, programs mean symbolic expressions. Those are then wrapped within some, in our case, an error minimization context where we do parameterization through a multinomial regression. And then the system will construct these multinomial expressions to minimize that, the kind of relationship between predicted workload states and the observed labeled workload states. And the error minimization function we use there is, in the case of the one we're talking about here, is a maximum likelihood function, but then we penalize it with the complexity of the underlying model. And when doing this, and it can be seen in our 2019 paper, which I'll present at the end of the citation list, is we were able to see one in very strong performance in terms of predicting workload states. But the most meaningful things that we saw were, one, when we compared that to using just the task labels, the task labels could be valid on the training data set, but then the second they were applied to a holdout validation set, they were essentially useless. Whereas our models trained on the let's call it capacity informed labels maintained a high degree of transfer to new individuals as well as to new tasks. And then the big test was showing that it transferred to a new individual performing a new task that was similarly stressing to the task the algorithm is trained on. And then the other advantage is when you look at the models, you can see, okay, what is the symbol that's being used? How does that relate to then the different channels that are in the fNIRS device's sensor for measurement? And then we can see what are the differentiations between states and how these matter. So I want to highlight that this is not like what one might see if we trained a deep neural network on this problem and then used some of the new linearizing techniques that have come out of explainable AI, such as Shapley's additive values, which are trying to formulate a linearized model of that deep neural network such that one can interpret the feature space. These are the direct features. So there is no mismatch between a linearized model and some deep nonlinear model. This is the direct model the algorithm is using for then establishing those states, and it allows us to then look back and compare them to things in the literature that might be seen on previous workload studies. All of this taken together, once we had done this and we'd replicated it from the memory domain to the perceptual domain and the attentional domain, we had high confidence that even though we've built a classifier that is sufficiently performant, that we can start applying it to real world diagnostic tasks and start to move past just building a better classifier to starting to ask the harder questions of, okay, now that we can measure and recognize relevant states, what can we do with it? And I think, Brenda, that brings us to the poll. I don't know if you need me to stop sharing or how you want to.
can just, yeah, hold on to that slide. The poll will appear above that.
Okay.
And then you don't have to worry about, starting and stopping or screen sharing. Okay, so I'm going to go ahead and launch this poll. And yeah, we're interested in hearing about what you wish you could do with psychological or brain-based measures, excuse me. So we'll just let people answer that poll for about 60 seconds. And I'll go ahead and present the results in a minute. Yeah, so just so everybody knows, if you have a question for Dr. McKendrick, feel free to ask it. We'll probably save a couple questions for the end. It's going to be a pretty full presentation, so I don't know how many we'll get to, but if there are questions, we'd be happy to share a question and answer document, after a week or so after the webinar. Okay, let's take a look here. Looks like we have a lot of people in medicine. Okay, great. I'm going to go ahead and end and share the results just so you guys can see them real quick. Lots of people. It's a mix of people, but mostly heavily in medicine. So thanks for sharing, and back to you, Dr. McKendrick.
Okay. So with that, let's transition to the application of this system that we were looking at. So a couple of years ago, we got interested in looking at doing guidance assistance for Black Hawk pilots and copilots. I think many people don't know that the US military, namely the Army, faces a lot of their Class A mishaps, which are essentially big accidents, during training. And there's a real challenge in training Black Hawk pilots and other rotorcraft pilots because rotorcrafts are really complicated, much more complicated than a fixed wing aircraft. And it's very easy for these mishaps to happen. And a common thing we would hear about is just being heads down, dealing with degraded visual environments, all these things. So we wanted to explore, could building an autonomous guidance system that's constantly informed by the state of the human operator potentially provide some benefit. And I don't know if for those of you in the US that are watching the news, there was obviously a very recent tragedy just a couple of miles from where I live. There was an accident between a Black Hawk helicopter on a training exercise with a commercial airline. It was really bad. Both crashed into the Potomac, which was freezing at the time. I don't want to misrepresent the system that we're developing and make any kind of claims that some of the research we're doing here could have in any way kind of averted that accident. But I do want to highlight the importance of this research and kind of acknowledging a lot of the human factors challenges that are present during these training exercises with Black Hawk helicopters, especially in, when they're in the US and within vicinity of civilian air traffic. So with that, the way we had structured our study is we had a Black Hawk simulator, and we were able to represent many of the tasks that are involved in interacting with that physical system, not necessarily piloting it, but interacting with the many menus and system controls and things that one does throughout these phases of flight, namely being on the ground during pre-flight, getting ready to take off, climbing to a cruise altitude, maintaining the status of the system and performing navigational tasks during flight, and then eventually selecting your approach and landing safely. So some of the guidance procedures that our system was taught to do during pre-flight is kind of loading the mission data, confirming databases, performing avionics checks, checking the engine management system, checking for mission setup, establishing kind of the basis of the flight platform, and then providing a no-go decision to the pilot to determine takeoff. During nominal flight, what our system was designed to do is help the pilot do their cross checks, monitor their avionics and their mission, monitor the route and flight parameters that they were interacting on, and being able to communicate status both with their fellow pilot as well as over the radio. And then finally, we also created a number of issues, weather alerts, engine malfunctions, and data miscompares across elements of the system, and our guidance agent was there to help individuals navigate those. The challenge of building a guidance system like this means that you're essentially building a robot. So the core of our system has two components. It kind of has the outside sensors of the robot, and those represented the world states that the robot cares about. So things like the events in the Black Hawk simulator, the data coming from the fNIRS and the workload states, and then any other sensors we had. So the displays on the augmented reality device, which I'll be showing, its sensors. It's the head position of the individual, their eye gaze, any button presses, things of this nature. So those all would come over what's basically a ROS2 network, which stands for Robot Operating System. And then that data bus would facilitate interaction with a knowledge base, any user modeling that we had, the explicit user guidance, how procedures that the pilot is going are grounded in that knowledge base, and then how those procedures get grounded in the environment, namely the context of the aircraft and its systems. Crafting the knowledge base was a bit of a challenge, but fundamentally for reasons that I'll talk about in relation to the large language model that we used, we wanted to ensure that the knowledge base had explicit concepts. These were associated with English terms that we could use for grounding those concepts and interactions. And fundamentally, those are stored and manipulated as facts and follow this structure of triplets, namely subject, predicate, and object. And we're able to structure them this way. And they kind of allow us to navigate a tree like this to then establish the procedures that the operator is doing, what procedural steps should they be on, and should we intervene. So like a worked example for this might be, there's the UH-60 system. It has a number of properties. There's the term UH-60, and then we have things like the inboard and outboard multifunction displays, which are labeled here. They then have their own characteristics, et cetera, et cetera. And then by backtracking through this tree, we can then establish what a procedure might look like, which is, okay, given the current procedure, you should look at a specific multifunction display. If not the primary display that you need to be on, you need to toggle it with a certain input, and then perceive the current stimulus that is required for you to move on, given a procedure. this whole system then needed to be instantiated. So the way it got instantiated, as I mentioned, ROS, that is kind of the data bus, but that needed to interact with the HMI device, or sorry, excuse me, the augmented reality, or in this case, extended reality device, which we use to project an immersive world around the pilot. And so that was implemented within Unity. The augmented reality device that we were using was a Magic Leap 2. And then what we would do is affix under that the BioPack system, which would provide the real-time fNIRS measurements, which would then go to our Python backend, and we would do all of our processing, which would then pass over into ROS, and then from ROS over a bridge into Unity, such that all of that could be integrated into the final system. And so here's an example of essentially what the pilot would experience when interacting with the system. It was actually more opaque than this. And what we were particularly proud of, because it was very hard to facilitate interaction with this system, and we needed to make this basically fully interactable cockpit mobile. So what you're actually seeing on those displays is not virtual. Those are actually physical displays that are touchscreen displays that are then embedded into the extended reality world. And I think I have a better image of it like this. So you have these physical systems that you would interact with via the touchscreen, and they were mobile, and they would emulate the mission computer, the Black Hawk, and then we would immerse the individual in this scenery and scenario so that we could do testing of this system. So that brings us then to the LLM agent that we wanted to explore, because we wanted to start with, given the knowledge base, this basis of procedural guidance. But we wanted to adapt that procedural guidance in real time in an intelligent way. And instead of exploring building up all these heuristics around how to do that, we wanted to explore, both for purposes of future research and for the limits of such technology, could we take an LLM, a large language model like you see with something like ChatGPT? In our case, we took a very small one, Phi 3 made by Microsoft, and we fine-tuned it using operational manuals and some of like the concepts in research around cognitive science, and gave it these kind of 3 phases where it gets instructions given the manual. It is provided some few shot examples of how to use adaptive context, and then it gets in the real-time context 10 seconds of cognitive workload history, a representation of the pilot's current tasks from the knowledge base, as well as then where the pilot is looking. And it takes that information, and that goes into a prompt, and then it decides how to modify the rigid guidance that our rules-based knowledge base provides, and then alters it in such a way based on the prompt to determine was there a better way to present that information to the pilot to elicit a better cognitive state and a better response. So it kind of ends up looking like this, where you have, at least from the perspective of how the real-time workload is used, is you have the fNIRS time series, which goes through a sliding wavelet filter to then get rid of any motion artifacts that you commonly see within the fNIRS response, as long as other physiological artifacts that are not neurological based. Those then go into our 3 independent classifiers for memory, attention, and perception, and then the relevant states for that are output along with a confidence variable. That then goes into the ROS robot operating system, which then pushes to the back end, hits the classifier. Those are then established as world states. They're grounded in the procedure, but then all of that goes into the LLM, which then provides back the new guidance, which then goes back out to the robot operating system, which passes it over. In this case, for the study, we were using a Quest 3, and then is projected to the pilot on their interface. So the study that we then performed to validate this system, we brought in both students and ex-rotorcraft pilots. We had them perform a subset of the full set of tasks that we had developed for the system due to time constraints. And they then experienced 3 different guidance modules. One was a checklist, which was meant to emulate the current knee boards that pilots use today to go through emergency and in-flight procedures. The other was an adaptive system, as I mentioned, that was using their real-time brain state, providing the guidance that I've mentioned using the LLM. And then the other emulated the adaptive guidance system. However, the guidance it provided was completely random and ignorant of any of the neural states of the individual, but did everything else that the adaptive system did. So when we then compared, what we found is in the baseline context, they perform tasks at a certain degree, right? This is kind of our baseline. And then in the random, we saw in some contexts, just providing random guidance significantly hurt completion time of the tasks. But consistently, what we found is that the adaptive system was either on par or significantly faster in a number of cases than the baseline context. And in this graph, the bars as they move to the right essentially are more complex procedures. So what we can see is in a lot of the procedures near the end that pilots had to perform, the adaptive system actually accelerated their ability to execute those procedures. The other element that was really important to this is that at least in two of the cognitive facets that we looked at, we did see significant differences than in the observed states when being presented with adaptive guidance. And the biggest one was in their memory states. And what we saw was that under the adaptive condition, pilots spent a significantly greater amount of time in an optimal state, a state that shouldn't produce errors, as opposed to the baseline condition where they experienced greater amounts of overload, and the same thing with the random condition. Now, what then segues into some of the things that I think we need to work on scientifically is if we look at the perceptual case, though. So this was the algorithm that was trained on stimulus degradation. Is what we saw is it wasn't significant, but it was significant, but it was certainly trending in this direction. Is that in the random case, participants had better workload outcomes, namely spending more time in optimal load than they did in the baseline condition. And when we look at the data, they also look like there was a slight advantage over the adaptive condition, which perhaps suggests that for certain cognitive facets or modalities, we need to implement different guidance or control methods. And that's why this was a validation study, just to kind of get started to really show that, yes, you can do this, but the next step is how do you do this correctly? And that's kind of what I want to focus on here is, as we applied this adaptive system within this real world context, the goal here was not to prove out whether or not the working memory classifier was perfect. The goal here was to prove that when applied on a task like this, did it enhance performance? It did. Were we able to modify the primary control state that we wanted to modify, namely time spent in optimal load? We could, but we couldn't do it perfectly. So now the question then becomes, how can I continue to understand how to change that cognitive state input for the better? How do I tune this controller? How do I tune the feedback mechanisms to the human such that I can produce the system outputs that we desire, namely increased performance envelope, as well as then some of the other things we want to start exploring is not just how do I tune feedback to the human, but how do I tune feedback to other internal controllers within the system? And I think these are some of the next things that my lab is going to be looking at. And I think if you're interested in some of the concepts that I've briefly addressed here in the talk, there are 3 papers that we've worked on. One is the adaptive Copilot paper, which I mentioned here as our validation case. 2 of the theory papers that have kind of led to the development of this system are presented here. And then if you're interested in knowing more about genetic programming, symbolic regression, and this new kind of frontier of doing supervised machine learning and equation discovery, I really recommend the Field Guide to Genetic Programming by Riccardo Poli and colleagues. And I think with that's kind of my time. So we can transition to questions or whatever you like, Brenda. Should I stop sharing?
Let me just leave that up there for a minute. Let me go ahead and we had a second poll, so I'm going to go ahead and launch that poll.
Okay.
And then which of these are you most familiar with? So let's just hear back from everyone. It's multiple choice, so you can have multiple interests, just so you know. Just give them a minute to answer. And we'll go to Tim after this. People are still answering. And give that another. Okay, looks like almost everybody's answered. So it looks like it's heavily, people are most familiar with machine learning, brain imaging are the top two, with extended reality coming into a third, and then generative AI and none being the smallest amount. So go ahead and end that poll. And now we will switch gears and head over to Tim. Tim, I'm making you presenter.
All right. And this will be really quick, so we can dive into questions in just a minute. But we just wanted to quickly touch on the systems that obviously he's been talking through this entire time, which are the fNIRS systems from fNIRS devices themselves. And so this is just showing the 3000 module, which can connect to either the 18-band full forehead sensor, which is pictured here. There's also a smaller 6-channel sensor, and just the cables that come with it to basically connect that sensor into the system itself. Every system comes with the fNIRS software that was mentioned as well. This is a specific picture of the VR sensor that was created to just help with connectivity and ease of use and comfort for the subject if you're wearing an HMD or an AR headset. And it just kind of extends the little bands down here. So instead of plugging in back here and creating extra things to go under the bands, which can put pressure on the head, it just takes that pressure off so that subjects can be a little bit more comfortable for a longer state of time during data acquisition. So that's kind of a nice custom utility that was made from fNIRS systems specifically for Dr. McKendrick that is now available to all. And speaking of virtual reality, obviously in his context, he was using Unity, which we do have plugins. And so obviously Unity is able to be used with fNIRS devices, and obviously the HMDs and Acknowledge and everything like that. We have a plugin, but we also partner very closely with WorldViz Systems, which is the creator of the Vizard VR technology, which could also be employed for such things. So if you have any questions regarding that utility, definitely feel free to contact us. And again, you can look this system up on our website. And again, this is just the 3000 model. There's actually another larger model as well that can do multimodal and a full mobile system as well. So subjects are out in the field and you need to collect under real life circumstances versus in lab. And that's all I have.
Okay, so then let me go ahead and share my screen again. I have a couple things I want to cover. And this is, we don't have a lot of questions, so I think people are really just spending time absorbing the content, but I do have a couple questions that I'll share. All right, so before we get into the Q&A, I just want to let everybody know that BioPack has produced over 100 webinars, including a bunch of, fundamentals related to fNIRS technology. And you can go onto our website. It's just biopack.com/webinars to access any of these webinars and watch them at your convenience. Also, if you just like to talk to a sales rep so you can learn more about it, we have regional reps all over the world. You can just scroll down on any page and find your regional rep. Mine is Amy because I'm in California, but yours will be displayed here on this page. And if you submit this form, it immediately sends them an email. And then if you search for fNIR on our website, you'll get access. This is the system that Dr. McKendrick used. There's a newer system that's coming out in the next month or so. And then, of course, we have the mobile system. And then finally, here is the VR. This is one of the VR packages that we offer using Vizard software. And This one includes eye tracking, but there's some various customization options there. So, okay, so let me just get back into my presentation here. Okay, so so hi James. He said this was amazing. Thank you. And then Vinay asked about cultural diversity in the data sets for symbolic regression analysis. Was there any cultural diversity included?
Yeah, actually, so while cultural characteristics were not an explicit modeling factor, one of the advantages that we have, or that I believe we have working at a very large corporate entity, unlike, say, in a university setting, is there were people from different educational backgrounds. The age span that we had was from 19 to 65 years old. And then granted, they were all American citizens, but a number of people from different ethnic diversities as well. So it was a very diverse data set.
Okay, great. And let's see, questions are coming in. So this is coming from Andrew. First of all, nice presentation and impressive work. He's curious why fNIRS was the measure used for cognitive classifier. Also, how were motion artifacts in the fNIRS data handled during real-time operation?
So actually, mostly because I've been doing fNIRS research now for the better part of a decade. That was one choice. In my experience, outside of dry electrode EEG, when needing a measure of the central nervous system, I found fNIRS to be the fastest to set up and do data collection. So there's both my bias of I'm very familiar with the technology, and I think it's fundamentally very fast to set up. In other research I've done, it's really robust to motion. So we've done a number of ambulatory studies outdoors, and while you do need some artifact filtering, it's not much more than. So as an example, in that study, we had people sitting doing a cognitive task, walking indoors doing a cognitive task, and then walking outdoors on a crowded university doing a cognitive task. And while we did have to do some motion artifact filtering in those cases, it was post hoc, the methods and degree of filtering was not vastly different across those three contexts. So in my experience, we've had good performance with fNIRS in that case. In the case of the real time, what we did, and it's in our 2019 paper, and you can look up some more of the details, although we've never published like an explicit study on how we did it. So we actually use a sliding window wavelet filter, and we had to adapt wavelet filters to then be able to do that in real time. And that's how we do the motion artifact filtering for our fNIRS system. A number of studies had shown kind of the validity of wavelet filters for reproducing the original signal relative to some other filtering techniques. I didn't mention it, but so with that running in line with our workload classifier, we are able to produce a workload state prediction at about 2 hertz. So we reproduce two predictions every second.
Okay, so a couple people asked similar questions here, so I'm going to summarize. John asked specifically about utilizing EEG in this scenario. Did you choose fNIRS from a practicality point because of the electrical noise with EEG or other parts of the setup?
So yeah, it was mostly just ease of setup. Granted, there are a bunch of really good dry EEG systems out there. It's also just in our previous research, right? We had been doing it that way. I think EEG could absolutely be used in this context. I think the big differentiator here, although this needs to be validated, is not so much the physiological sensor, as long as it's using a measure of central nervous system. I think there have been enough studies comparing EEG and fNIRS, and that they're either complementary or if you need to use one, you can probably get away with one. I think the big differentiator here is actually the labeling methods that we used for doing classification. So if one wanted to apply those methods to an EEG system, they should work just as well.
Okay, so I have a couple questions from Brittany, and then we'll probably have to wrap this up. So if there's any urgent questions, I need to have them come in right now. But so Brittany asks, this is a two-part question. I'll start with one. Do you think your results for the perceptual task was related to the modality of the perceptual task, visual versus auditory? And would you anticipate a different result based upon the modality?
So the classifier is trained on the visual modality. We haven't done one for an auditory modality. The guidance that was presented was actually multimodal. It was both visual and auditory. So from that perspective, yeah, it is likely that because the guidance was multimodal, there could have been a benefit. I also have been wondering, as I've looked at the data, if there's some timing characteristics due to how we're presenting the guidance that for some reason regarding the perceptual classifier was producing a benefit when the guidance was presented randomly as instead of based on the state. Actually, something that we mentioned in the paper that I did not mention in the talk was one of the limitations of the large language model. So the large language model commonly, even though we provided a very explicit guidance on the difference between attention and perception, because these models are fundamentally trained on Common English, it often struggled to understand the difference conceptually in terms of how to provide guidance when somebody was perceptually overloaded versus attentionally overloaded. And we're also looking into that as well to see if that contributed to some of the discrepancies in the perception state results.
Okay. And any thoughts on different psychophysiological indicators that could be good for perceptual tasks?
Oh, I think there's so many. We just focused on workload. Another one that we're looking at that I think is going to be interesting because we think it's associated with workload, but it's not quite the same, is frustration. So we're doing another task where we're exploring looking at the biomarkers that might be associated with how frustration impacts you, because we think it might be something that, okay, given the workload you experience, your workload capacity might actually be affected by whether or not you're in a state of frustration. If you're more frustrated, maybe you can't handle the same processing demands that you could in an unfrustrated case. So I think that is also kind of an avenue that needs to be explored, is kind of continuing to map and build initial classifiers or tools for measuring these different states that we know that are relevant for human performance.
Okay, so last question. During the course of working and building this system, what were some of the challenges that you faced?
The biggest one was integration with the augmented reality systems, namely because either those headsets would kind of be available and then companies would stop supporting them, or there were just constant software updates, and it was very difficult to maintain constantly working branches of our code base because of how brittle those systems were. And it was really difficult to deal with when we're building all this new technology, and a lot of it is incredibly custom, and everything works except the commercial mature technology in your system. So that was an incredibly frustrating part about integration. And that's obviously SANS doing all the challenging science, but it's like from an integration and engineering perspective, that was the hardest.
Okay. Well, okay, let's just see something. Are there any learning resources or open tutorials with learning more about fNIRS? So as I mentioned, we have a bunch of webinars that talk about fNIRS. Is there any other source resources that you know of?
I think those are probably great starting points.
Okay.
At the same time, every couple of years, there's the neuroergonomics conference that's held in the US and internationally. BioPack is usually a sponsor. If you want to meet me and get a drink or whatever, I'll probably be there. I think the next one is going to be in the US, and they often will hold tutorials for fNIRS and other relevant technologies there.
Great. Yeah, it was just this last year, so it won't happen in 2025. So
Yep.
look for that in 2026, and you can always go to our calendar and on our website, and it will be listed there usually. So, all right. Well, thank you. Let me just take a minute to let you guys all know that we host webinars almost every month of the year. You can watch them at your convenience. You can also join us next month. We'll be talking about eye tracking, and there's some new software that's available with our eye tracking system for analysis. We also host web workshops, all over the world. So if you're interested in us coming to you to bring some equipment so you can get a team at your organization or regional area, they can come on site and we can host a workshop there with you. It's a great way to learn about the options and get hands-on experience with the equipment. Of course, you can come to our 4T conference, 4T Fizz in July, where you can access all of the equipment here in California. Today's webinar was recorded, and we'll send each of you a link once it's processed.
I think she locked up. I think she was just going to say, if you do have any additional questions, feel free to email us and we'll get back with you. And I do think the slide deck will be able to be made available. We had a couple questions on that. So thank you everyone for joining, and we will see you next time.